Hello, welcome back. So in this last part, we're going to look at some famous models called BERT and some variations of a model called GPT, which fall into the category of transformer-based models. So as you'll see, these are quite heavy models in the sense that these are really big and deep neural networks. And we're going to start with BERT. You can see that a lot of these models are named after Sesame Street characters. So there's Bert and Elmore and Ernie and a few others like this. BERT, as you might know, was developed by Google and was first released in 2018. So they had a publication about their open source version of BERT. And this falls in the category of pre-training for natural language processing. So the idea of pre-training or transfer learning is that you have a model that you first build in a semi-supervised step. So the typical example of BERT is it's trained on all of Wikipedia. So have a huge amount of knowledge in English, for example, but also in other languages. And then you pre-train a model similar to what we did with word embeddings. So you can do this in a semi-supervised step. At this point, the model is just learning all the information from Wikipedia. It's not trained to do a specific task. So this is quite expensive. It's a big model, but once you have this model here, this pre-trained model, you can then apply it to multiple different tasks. Essentially, you're adding one or multiple additional layers, and then you do a supervised learning step. So you feed your input first into BERT, then you take the output from BERT, it goes into your additional layers, for example, for a classifier, like here, simple spam classification. And here you have a specific data set to train this final layer on this specific task. So there are quite a few adaptations of BERT. So the classical BERT, like I mentioned, is trained on Wikipedia, but people trained using the same network architecture, different variations of BERT. So there is SciBERT trained on scientific publications. There is video BERT on YouTube videos. If you take biomedical documents, you get BioBERT. And there's also Ernie trained on a knowledge graph as input. So then you have these pre-trained models, and then you fine-tune them for a specific task. For example, classification, relation detection, or named entity recognition. And there are lots and lots of models that people used for different tasks. There are whole startups that all they do is they take these pre-trained models and then adapt them for a specific use case in a company and apply them to this task. As one example, BERT was used on this task I showed you a couple of lectures ago, this question answering task using the Stanford question answering dataset. So here the task is that you have a given text, and then for this given text, you have to be able to answer a number of questions, like which type of climate may have allowed the rainforest to spread across the continent. And then after reading this text, you have to be able to predict the correct answer. So BERT was applied to this question answering task as well. And that was one of the significant results at the time, 2018, that BERT achieved an F1 score of 93. So at that time, it was not only better than all the other systems, including another one from Google. So it beat them on the F1 score, but also for the first time was better than human performance. So yet another task where AI was finally getting better than a human on the same task. So BERT was a very influential, it's still a very influential and successful model, and in particular because Google open sourced it, people used it for all kinds of applications. Now, when we say open source, you have to be careful. So far, all the models that we looked at are more or less possible to train on your own system. A bit faster if you have a GPU, but most of them were still manageable. In the worst case, it takes a couple of hours or days to train. However, BERT is now such a big model that you need some serious hardware behind it. So in one reference I found is if you want to train BERT in this BERT large version, you need a DGX2 server, which is an NVIDIA server architecture, which has 16 GPUs of type Tesla V100. So this is a GPU not used for, they don't have any kind of video output. They're really used just for AI purposes. So with 16 V100s, it still took 3 days to train. And a V100, if you can buy one, I think they go for around $9,000 for one card. So if you buy 16 cards and then you have to buy the actual server that can run these 16 cards, you're looking at maybe $250,000. And then you still have to wait 3 days just to do one training experiment. So if you want to do it faster and not wait 3 days after pressing model.fit, you have to invest even more in hardware. So this is quite heavy. Basically, you can forget about training this on any kind of normal home setup. You could do it on cloud infrastructure, but then again, you pay quite a bit of money for using large-scale cloud computing GPU resources. The good news, on the other hand, is that there is a large open source community around sharing these pre-trained models. So there's one company that's well known, Hugging Face, which has both cloud computing resources where you can use the models on the cloud and pay some money, but they also have a lot of models that you can download and use yourself if you have a system with enough memory. Remember, what I told you here is about training the model. Once the model is trained, just applying the weights that you have learned doesn't need that many resources. So even though BERT is very expensive to train, you can still use a BERT model and run this on normal, normal desktop workstation computer grade hardware. So we'll experiment with some of these models in the last lab. To show you how Google is using BERT, so in 2019, they integrated BERT into their Google search, starting for the English language. And it was used, or it's being used for understanding the question context better than Google understood it before. So for example, here in the question 2019, Brazil traveler to USA need a visa. And the old style Google model would take this question and give you lots of results about can a US citizen travel to Brazil without a visa? But if you look at this question, this is not what the person asks. It wants to know a traveler from Brazil to USA. And after using BERT, Google was able to much better predict what the search is about and give the right answer. In this case, the information for a traveler from Brazil to get a visa to the US. Another example, somebody searches for, can you get medicine for someone? Pharmacy. So when you read this, you can really see the person sitting there and you know what they want. Yeah, you want to ask, can I get someone else's medicine at the pharmacy? Yeah, not my own, but I have the prescription for someone else. And before BERT was integrated in Google search, you got the results that you would predict. How do you go to a pharmacy to get a prescription filled? Well, you have all the words in there, medicine, pharmacy, but this is not the question that was asked. And after integrating BERT, Google can now much more precise answer this question. Yeah, For example, it gives the result, can a patient have a friend or family member pick up a prescription? So this was just integrated in Google Search for English starting in late 2019. So just a bit more than a year and a couple of months old at this point in time. So what you can see is that this type of model is now becoming quite big. You've seen BERT. If you want to train it, you need some serious hardware behind it. So it's starting to get out of reach for just students that want to do an experiment. A well-funded startup could possibly still raise $250,000 or a bit more to get hardware if they're building these models all the time. So you can see in terms of complexity, these models are getting significantly bigger. Remember, we started with image recognition in the very beginning of this talk. So what you need for things like Google Photos and other tools that scan images and automatically find entities in there and create these catalogs of images, but also the kind of network you need for autonomous vehicles, self-driving cars, visual search, and so on. So remember, AlexNet was around 60 million parameters. Another network often used, ResNet, had 26 million parameters. Now, BERT in the large version is now up to 340 million parameters. So this is the one that I just showed you here. BERT large, where you needed 16 V100s to train it in 3 days. So this is the type of network you need for natural language processing, question answering, machine translation, and so on. So you can see that these are an order of a magnitude bigger than the networks needed for image processing. And since then, the models that we're going to look at next, GPT-2, increased the size again by another order of magnitude. The small version of GPT-2 has now 1.5 billion parameters, and there's even a large version of GPT-2 which has more than 8 billion parameters. So if you struggled with training these 340 million parameters, you can imagine how expensive it is to train an 8 billion parameter network. Before we look into what GPT-2 can do, again, a quick overview on what a transformer network is doing. So it's somewhat similar to this sequence-to-sequence model we looked at earlier. The goal is that we give in an input sequence. For example, if you want to translate this "we étudiant," we give it into the network, and we want to give an output in another language, like "I am a student." So that's the idea of a transformer. So internally, how they work, I explained in the sequence-to-sequence model. So basically, there is an encoder part and a decoder part. In a transformer now, we don't just have one encoder, we have a whole bunch of encoders stacked on top of each other, which then go into a whole series of decoders stacked on top of each other. So it's like the encoder, the sequence-to-sequence model blown up onto multiple dimensions. Now, inside of each encoder, again, you have two different layers. The input is word embeddings, just like before. They go to a special layer called self-attention, which basically help the network to focus on the correct word in a context of words. They then go into a feed-forward network and then go into the next layer. So this goes step by step through the different encoding layers. Then we have an encoding of this vector, which then goes into the decoding layer and then is being decoded step by step. If you go to this website here, there is a nice animation where you can see a vector going into the network and then being decoded into the output here. So GPT-2 similar to what we've done before with this LSTM network, can do various tasks. It can translate. It can also generate documents. And maybe some of you might remember one of the news that ran around on tech blogs and magazines and even in non-technical news was the kind of stories it could generate. So just like before, remember LSTMs, we have to give an sort of a text sequence, an input sequence to start the generation. And you might also remember that what we generated just based on this Aesop Fables text corpus was not that impressive. So here in this example that the GPT people published, they fed in an input text. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And then the network started generating output. The scientists named the population after their distinctive horn, Orwitz unicorn. These four-horned silver-white unicorns were previously unknown to science. Now, almost after 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. And you can see that what it generates here is an almost perfect story that a human could have written. So this was a level of capability of text generation that was previously unknown. And basically, it is trained on a huge amount of text corpus, not just Wikipedia, but basically everything that you could scrape off the internet in form of English text, and fed into this huge multi-billion neuron model, which can then generate cohesive output. Another example, and here you can see where this might get critical. Let's say you feed an input like, for today's homework assignment, please describe the reasons for the US Civil War. Something like you might have had to write as an essay in school. And from this input, again, it will generate a coherent description of this question. It is easy to identify why the Civil War happened because so many people and so many books and so much television and films tells us that it was the cause, that it has something to do with race or economics or religion. So you can see it's not 100% perfect, but you could probably hand this in as an essay as a 4th grader, 5th grader, and get away with it. So back then, when GPT-2 was announced, it was again a bit more than a year ago, 2 years ago, 2019. They showed these examples, showed how they trained it. You can read the blog post in this URL here. But they said, we cannot publish this model because it's too dangerous. And that's quite interesting in the context of AI, right? Saying we have made an AI that is dangerous. And they said it's dangerous because with this level of text generation capability, you can have people generating anything they want. They can generate all kinds of fake news. They can generate legit-looking emails for phishing purposes or identity theft. You can generate tons of tweets in a certain style to manipulate social media, like generating tons of tweets for a certain topic and flood the social networks. As you might also guess, just telling people, look, we've built this great tool, but we're not going to give it to you because it's too dangerous. This didn't go over well. And there was for research purposes, very heated discussion. So as an example, I picked this tweet here from 2019, where a researcher answered, what you are doing is opposite of open. I'll talk about OpenAI in a second. It is unfortunate that you hype up, propagate fear, fraught with possibility and scientific endeavor. There is active research from other groups and unsupervised language models. You hype it up like it has never been done before. So there was a very heated discussion in the community around what it means to have a model like this. GPT-2 was eventually released in almost a year later, Moodle in February, they open sourced the smaller version, a 5 billion release in November 2019. So again, quite new. And yeah, people can use GPT-2, but you can see from the size, you need an order of a magnitude bigger resources if you want to train it yourself. And you need quite significant resources, even just for running this model. OpenAI, by the way, if you have never heard of it, is an institute that was founded by a number of famous people, including Elon Musk, Peter Thiel from PayPal, and a number of other famous people. Look up OpenAI online and read a bit about it. Originally, the idea of OpenAI, as the name suggests, was that they make AI research available as a public good, as a shared resource for others to build upon it. This has changed, however, because you might think GPT-2 with its size is the end of what is possible, but they beat themselves by releasing GPT-3 less than a year ago. So GPT-3 is the same kind of architecture, but now it's even bigger. It's a network with 96 layers and now has 175 billion parameters. Various people have tried to estimate what it costs to train a model like this, of this size. And using cloud computing resources, they estimate training it once costs roughly $5 million US. This is not the hardware, which would be even more expensive. This is just if you rent the cloud computing resources, the GPUs to run the training. You know, what you do yourself when you say model.fit, enter. Now you pay $5 million to let it run once. Even the model, once you have it and want to just run it to predict your input, costs you roughly $87,000 in cloud computing costs, taking the pre-trained model and applying it to new data. So this is now way beyond anything that can be reasonably done by even a large company. And OpenAI gave up on the idea of being open and went from a non-profit to a for-profit in 2019. So GPT-3 is available, but it's only available if you register for a paid cloud API. And another big tech news not so long ago was that Microsoft got an exclusive license to the GPT-3 source code. So this tells you that this model is now so big that even a large company like Microsoft, instead of trying to train it themselves, just licenses from OpenAI. So because they exclusively license it, they don't have to go through this public cloud API. They can access it themselves, and other people can still build on GPT-3 and use it for all kinds of applications. Again, trying to visualize the size difference. Down here, number of billion parameters. We have BERT, which we just talked about being way too large for you to train. And now in GPT-3, again, we have an exponential increase in the number of parameters that you have to train. So the interesting news is that GPT-3 is basically trained on anything they could get their hands on the internet, not just in one language, but in multiple languages, not just text, but also code. Basically, it's trained on anything they could scrape from the internet. And this transformer architecture can be used for all kinds of different tasks. It's not like BERT, where you have the pre-trained model, and then you have to adapt it to a specific task. You can use it directly. You can use it for text generation. You can use it for a language translation. You can translate text to code. For example, people generated HTML code layouts with it. It can be used for question answering, for chatbots, for summarizations, and so on. So you can see some of the example applications here, and on Moodle, I'm also linking some more videos with demos on what people used GPT-3 for. One example video that you can check out is the one here, where they used it to generate press releases. Now, when a company announces a new product, they put out a press release, and one person tried out to generate text that looks like press releases, but giving it interesting concepts like Tesla's new flying car. So have a look at the results that GPT-3 now generates. So this brings us to the end of this course. And let's go back to the very beginning. Remember, in the very first lecture, I showed you Eliza, this chatbot that would try to simulate a conversation between a human and a psychotherapist, but now you know how this works in detail, and you know that it doesn't really understand anything. It just applies some transformations to the input and gives you some answers. GPT-3 now has come a long way. It's a billion times more complex than Eliza, but in terms of intelligent system or artificial intelligence, it still doesn't know anything. It's just predicting output sequences, probabilities based on a huge amount of examples it has seen, but it really doesn't understand anything about what it's doing. It doesn't have any concept about the world, cannot really reason independently. As you've seen from the size increases, maybe it's possible to get this up once more to a GPT-4 type of model, but at the moment, this is kind of a dead end. The amount of resources you need to train it, if you look in terms of environmental impact of large models like this, it's not really sustainable. Of course, this is just one architecture, this transformer type architecture, and people are working on other type of architectures. So on the one hand, it's extremely impressive what these models can do now. On the other hand, there's still a long way to go in terms of new ideas for new types of architectures, new types of learning, and new types of applications. So we are at the end of this course on intelligent systems. I hope you got an idea on what kind of systems you can build. You know how to solve a number of interesting problems using one or multiple techniques that we have done. For this last lecture, I'm not really giving you any required reading. What I've showed you here, you can find in the toolbox that I also mentioned last time, the generative deep learning and our natural language processing in action. But because it was all on such a high level and it's the last lecture, I'm not giving you really required reading. However, you do have to have an understanding of the high-level concepts that we talked about here. With this, I'm going to say goodbye. I hope you enjoyed the course. I would be interested in any kind of feedback that you have about what you learned from the course, what you would like to see changed. Remember, this is a rather new course. It was given the first time last year, and last year only partially because of COVID. So I'm still working, updating this course, and I'm interested in hearing what you would like to get out of a course like this. So much from my side. Good luck for your further studies, and maybe I'll see you some other time. Goodbye.